Great. Thank you very much. Again, my name is Brendan O'Leary. I'm a product manager with GitLab. So I'm responsible for what we call Verify. It's CI, and then also all of the automated testing we do, so unit testing, performance testing, usability testing, system testing, and compatibility testing, which I should know off the top of my head since it's my responsibility. So today I'm going to talk a little bit about, excuse me, what Apollo 11 can teach us about DevSecOps, or kind of whatever we want to call what it is that we do. And so the reason I'm talking about it today is it was 50 years ago this June when Neil Armstrong and Buzz Aldrin walked on the moon for the first time, first human beings ever on the moon. But that was a feat that required an amazing amount of effort from hundreds and thousands of other individuals. Right? Even Neil Armstrong acknowledges this in his first words on the moon. That's one small step for a man, one giant leap for mankind. And the "a man" is debated. If you've ever seen the transcript, gets a little garbled, but Neil says he meant to say "a man," meaning that it was his small step, but again, a giant leap for mankind. So just to give us a little context, I want to kind of set where we were in the 1960s that encompassed the whole space race, right? From JFK announcing that we were going to go to the moon at his inauguration, all the way to 1969 when the space race ended with us making it to the moon. So this was a decade before Microsoft even existed. It was 40 years before Mark Andreessen famously said that software is eating the world. And just to put a finer point on it, 2001: A Space Odyssey came out the year before, so in 1968. And things that happened after the moon landing include Woodstock, which was August of that year, The Brady Bunch premiering on TV, so that was in September, and Sesame Street. So the first episode of Sesame Street wasn't until November of 1969. And, you know, the moon's pretty far. It's, putting it mildly, it's 238,900 miles away. And it's interesting to me because the original specifications for Apollo didn't mention the word software anywhere in them. It was all about the hardware. And I think that's an important point because of how a small group at MIT saw the world. So this was the MIT Instrumentation Laboratory, and they were the folks responsible for what's called the Apollo Guidance Computer. And the Apollo Guidance Computer is that thing that we've famously seen, maybe in Apollo 13. It's also called the disk key, so DSKY for display and keyboard. That's kind of the interface to the Apollo computer. And at first, when I was writing this talk, I discovered that there's actually a JavaScript port. Sorry, can we go back one? Yeah. This is the JavaScript port of the disk key. And because, of course, it's JavaScript. And at first, I was like, OK, I'm going to hook this thing up to GitLab and do some like DevOps demo with this. But then I realized how much bigger the story was. And that's really a story about Margaret Hamilton, right? So Margaret Hamilton would eventually be the director of the MIT Instrumentation Laboratory. She was born in Indiana in 1936, and she loved math because she didn't want to have to memorize facts. She wanted to be able to reason them. And she is quoted as saying that's because she was lazy. And I realized that it's really a story about her contributions to our field. So things that were under her guidance at MIT included all of the software that was going to be developed for the Apollo Guidance Computer. And really, at the time, her and her team really invented a lot of things that we think of today as we take for granted. So software engineering. The term software engineering as a discipline is something that Margaret made clear herself. She said that they needed to call it engineering so that it was treated with the same discipline that the rest of the engineering on the Apollo program had. End-to-end testing. So This is another thing that was really invented at that time. Asynchronous software, so the concept of having asynchronous software run. Priority scheduling in software. But then I think there's also two other things that we could contribute to this time. And so that's Agile. I think Agile was invented then, actually. That's my theory in this talk. And source control management. So let's talk about each of these. So it may seem kind of trivial now, and many companies use the term engineer interchangeably with developer or other terms. But again, for Hamilton, it really signified something very significant to her about how they were going to take the software very seriously as one of the life support systems on the Apollo missions. And it made me think of this XKCD, which some of you may be familiar with. Hopefully you can see it. You probably can't, but I've got the link there. And so in this XKCD, the conceit is that someone's talking to an airplane engineer about airplane safety, and they say, oh, it's the safest way to travel, the systems are so redundant. And then they're talking to a building engineer about elevators, same story. And then they're talking to a software engineer about voting systems. And the software engineer freaks out and says, don't use that, bury it in a field, wear gloves, and says, I don't know how to tell you this, but our entire industry is bad at what we do. So I think it's a lesson, again, in no matter what your title is, it's important to credit Hamilton with the creation of software engineering and all the disciplines around it as a discipline. And that kind of focused scientific thought is what I think can help us capture a lot of what we feel might have been missing in our industry. And so what does that mean? I think true engineering means understanding the balance between a few things. So the balance between error protection and fault tolerance, repeatability and adaptability, availability and reliability, and reliance and scalability. It's really in balancing these that we distinguish ourselves. And I think they're relevant for everyone involved in delivering software. Next, end-to-end testing. So end-to-end testing was nothing like it is today. It was a lot different. Hamilton said, well, we couldn't run something on the moon, but we could run a lot of tests on the ground. And before I tell a story about their testing, I want to kind of dive a little bit into the Apollo guidance computer to give you some context. So first of all, there's a video link again here that's great. It was a 1.02 megahertz processor. It had a 16-bit word length technically, but it was really 15-bit words with a parity bit. They actually invented a runtime interpreted language for this, really a virtual machine, the first virtual machine, so that the software engineers at MIT could write code for the processor more efficiently. And then it also had a shell, right? It was called Pinball. And that shell is what the disk key interacted with. And so that, and then it also had a remote shell that NASA could control from Houston. A couple more things. It wasn't quite as portable as the computers we have on our desk today, but it was 70 pounds. But every pound kind of matters when you're strapping something to a rocket, so that's critical. And then it was also the first to use integrated circuits and the first kind of computerized onboard navigation system meant to be used by humans and computers, right? So it was kind of the first fly-by-wire autopilot system. And then it had something called LOL memory. Exactly. So LOL did not mean what it means today. It actually stood for little old lady, right? So what this memory was, that's not a very nice term, but what it was really called was core rope memory. And it was called little old lady memory because it was actually woven into coils. So you take a wire and you weave it around these coils, through a coil's a 1, around a coil's a 0, right? Sure. And so they hired lots of seamstresses to do this weaving of the rope memory, and it would end up looking something like this. So you can imagine, so this is where the code actually ended up on the Apollo, was in this core rope memory. And so you can imagine the bar of shipping to production was pretty high. It actually meant that someone was going to go spend a couple months weaving your code into and out of coils. And thus, testing ahead of releasing your code was pretty critical. And Margaret understood this. So she spent hours in the simulator herself testing the software, but she was also a working mom, like our fantastic host today. And so she brought her daughter, who was 5 or 6 at the time, her name's Lauren, with her when they were working nights and weekends. And of course, her daughter wanted to play astronaut, because who wouldn't want to play astronaut? And they're in the simulator, and the simulator is kind of mid-flight, and her daughter puts P01 in. P01 is the pre-launch program, and that kind of cleared memory and really threw everything off. And Hamilton saw this happen and recommended that they place a protection in place so that mid-flight they couldn't jump back to pre-launch. It's like throwing the car into park when you're on 95. And what she was told by management was astronauts are trained professionals and they don't make mistakes. So we're not going to do that. So it won't surprise you to know that the next mission, Apollo 8, so Apollo 8 was the next mission. It's the first manned mission to go around the moon. It brings us this extremely famous photo, Earthrise, which is as the astronauts came around the dark side of the moon, the Earth rising above the horizon of the moon, right? Very famous. However, halfway there, another famous astronaut, Jim Lovell, of Apollo 13 fame, accidentally keyed in P01. So that erased all of the telemetry and position data from memory about where they were in space. And it took a couple hours for Houston to basically relay it by radio and reprogram in their telemetry data. So Apollo 9 had a software protection put in place, so you couldn't do that. And then I think two of the topics I was talking about, asynchronous software and priority scheduling, they came into play really with the mission we're all thinking about, Apollo 11. So Apollo 11, next slide. Apollo 11, this is it on its way to the launch pad in July of 1969. It launched on July 16th at 9:32 in the morning our time, because it's in the East Coast. And it takes about 12 minutes to get into Earth orbit. Once you're there, it takes about 4 days to make the transit. Again, it's 238,900 miles, or 384,402 kilometers. So it's a long way, but 4 days is actually pretty good. I was thinking about this morning. I've got 4 small kids, and my in-laws are about 1,000 miles away, and it takes us 2 days to get there. So the moon in 4 days is not too bad. So then, of course, July 20th, Aldrin and Armstrong make their way into the Lunar Landing module, start down towards the moon. But there was an issue with the radar system. So there's 2 radar systems on the Lunar Landing module. One's ground radar for where you're going to land, because you don't want to hit a rock. And the other one is called rendezvous radar. And that radar is constantly monitoring where the command module is behind you in case you have to abort. So with both of those systems on, it actually caused an overclocking of what the computer could physically handle at a time. It's getting too much data in. But Hamilton had built in an asynchronous, and her team had built in an asynchronous plan to the software and had hand prioritized each of the jobs very particularly. So the astronauts were actually alerted to this problem. They multiple times got a program alarm 1201, which meant the computer was given too much to do in a single cycle and caused a restart. But because of this, the folks on the ground knew what 1201 mean. Aldrin and Armstrong actually didn't remember in that moment, which you can't really blame them for. But they knew what it meant, and they knew that it meant the computer was handling the problem and prioritizing the most critical things. And so multiple times, if you listen to the audio of the landing, Armstrong or Aldrin reports the error, and Mission Control says, go, 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 because they know that it's going to be handled correctly. And so then, with 17 seconds of fuel left, they land on the Sea of Tranquility. And the rest is kind of history. But Hamilton's reaction, I think, is very much what we would expect and what I would say. She said, "Oh my God, it worked." And she's also quoted as saying that she was so happy about it working, but also most happy that it did the job that they had written it to do. She was most happy about the software. If you hear her talk about it, she says, yeah, Neil Armstrong was the first man on the moon. Our software was the first software to run on the moon. So she was very proud of that. And I think, again, those things, asynchronous software, priority scheduling, end-to-end testing, the term software engineering, those are things that you'll find on Margaret Hamilton's Wikipedia page, right? But I think there's a couple more things that we could credit that team with. And I think it's very foundation of how we think of software today. I think that was formed in these kind of extraordinary times of trying to bring us to the moon. And so I think they invented a little bit more than that. So Agile, as overused as a term it is, I think is something that really came about and is natural in the software process because it happened at the time. So this is 17 years before the term Scrum was ever published. And Hamilton's quoted as saying at the time that the very way you communicate can cause or prevent crashes. And so they would have these continuous improvement retrospectives. They would talk about what they were doing wrong, what they could do better. They would help each other define an error. How do we define what an error is? How do we know if it's catastrophic? How do we know who or what caused it? How do we know how bad it is? And I think even more basic than that, and relevant for me as I'm presenting, and I'm a GitLabber, is source control management. So again, this is years before there was such thing as source control management. But I think the very idea of like branching and all this that we do today was invented there. And this is why. So Hamilton actually had made a change to their main line, and the next morning, she had a line at her door, right? Because she broke something. Everyone's trying to figure out how to fix it. And so she said her solution was, we're never going to put a change directly into the official version. But first, we'll have an offline version to test. And so again, I think, the most famous picture of Hamilton you all will know is her next to a hard copy of the code for the Apollo guidance computer. So that is the actual code. It was actually confirmed by her later because it made it around to the internet and people were like, well, it's probably system logs. No, it's the actual code. It's 420,837 lines of code. Interestingly enough, 25% of that are comments. And it's about 11,000 pages printed out. So the question is, what can we all learn from this? How can we get back to what the founding mothers and fathers of our industry did, and how can we learn from their great triumphs? What is our moonshot, and how can we get there? So there's a couple things I think we have to focus on. First, don't assume the customer knows what they want, right? NASA's original specification had nothing about software. And so it's easy to see that they didn't exactly know what they needed. But just as important, I think, is don't assume that you know your user, right? Again, astronauts are perfect. They're trained. They're never going to make a mistake. We should never assume that we know our user well enough to make decisions for them. And we should blame ourselves if the user is using our software incorrectly. That's our problem, not theirs. And next, this is actually Hamilton's Lego. So you know you've really made it when they make a minifigure out of you. That's a critical time. But I think that I use it to illustrate. I think the key is to test like a kid playing astronaut, right? Test with the freedom, the audacity, the creativity of a 6-year-old who wants to play astronaut. That's where we'll really test the bounds of what we're trying to build. And lastly, I think we have to remember that we're standing on the shoulders of giant. Oh, that's actually the wrong Margaret Hamilton. Can you just one more? No, one. Yeah. Oh, nope, still wrong Hamilton. Keep going. Nope, other way. No, you're going the right way. Keep going. There you go. Okay, thanks. So. A solid joke. So remember that we're standing on these shoulders of giants, right? Like we talk about that all the time, but I think it's critical to remember that these were humans that did extraordinary things. And I think it's important to also remember to thank Margaret Hamilton. And, I was thinking about this, and I kind of had this as my last slide originally, and it wasn't quite finished. I was like, well, how can we thank Margaret Hamilton for this? And I think that's with the engineering mindset, right? If we bring an engineering mindset to what we do, we really are thanking her for being one of the mothers of this industry and instilling that engineering mindset in those early days of software. She knew what was at stake. She quoted herself as being too lazy to make a guess. And she taught us how to approach software and systems engineering as a true science. And because of that, she got to say that she was one of the biggest pioneers in our space and that there was no time to be beginners. Thank you very much. One more thing. The original code from Apollo 11 is on GitHub. Not a plug for GitHub, but that's okay. And someone actually reported the error 1201 and 1202 went in descent. So, but it was closed as one fix. So, right, thank you.